the collision of a car against the wall. It says in a particular crash test, a 1.5 times 10 to the third kilogram automobile crashes into the wall. The initial and final velocities of the automobile are initially minus 15 meters per second, so it's traveling in the negative direction, 15 meters per second. After it hits and bounces back a little bit, it bounces back at 2.6 meters per second. If the collision lasts for 0.150, 150 thousandths of a second, find the impulse due to the collision and the average force exerted on the automobile. So we have our velocity initial, we have our velocity final, and we know the duration of the impact. We also know the mass of the automobile. So all we have to do is start putting these together then in terms of momentum. So the momentum initial, the mass of the car times the initial velocity, gives me a value of minus 0.225 times 10 to the fourth kilogram meters per second. We observe the negative sign in there because, of course, we're going to use that when we take the difference in the two values, final and initial, but the direction of the automobile, just like we've done before, accounts for that negative and positive sign just by laying it on the axis on the number line, just as we've done before. We have to conform to those standards, those things that we have defined early in the course. So we do the same thing for the final value, and we end up then with the two momentum values that occurred before and after the collision. So again, what we're looking at is right here, where delta P is occurring over a interval of time. We haven't done anything with the interval of time yet, but at least we have this value that we can put back into this relationship and help us determine the amount of force in the impulse momentum. So we stick it back into the relationship. Since force is equal to the interval of time, or force times the interval of time is equal to the impulse momentum, which is really the difference, final and initial, of momentum. Take these two values, put them in the relationship as the difference between the two, and I end up with the impulse momentum, force times time, of plus 2.64 times 10 to the fourth kilogram meters per second. So now I know the amount of momentum here at the top of the curve, the product of this axis times that axis is all it is. If we want to determine the force, then again we go back to those values and this impulse momentum that we just calculated using the difference between those two guys, and now we integrate the duration of the impulse. How much time down here at that peak did the momentum, impulse momentum, create an amount of force? Since before we said it was the average, because we looked at it and said, well, we can simplify it really as to that rectangle. The average point should be right through the center on the y-axis, the f-axis, and we come up with a average force then of 1.76 times 10 to the fifth newtons. So it gives us an idea then of how many, or the magnitude of the force. In this case, if we move the decimal place, 176 k-newtons of average force in this problem. So we're just relying on this relationship so far to calculate the difference in the momentum before and after a collision, the length of time that it took for that collision to occur, in this case 150 thousandths of a second, to calculate the average force then from this relationship. Does this make sense? The graphical relationship is just there to help us see what's occurring in the fact that we've made this approximation then on the curve. Your text goes through an interesting example here of an automobile accident. How many of you have seen the video? I think Metro here puts it out here in town. If you watch one of the public channels on there, and they talk about what occurs step by step, second by fraction of a second by fraction of a second in an automobile, where they talk about the car hits the abutment or whatever, the back end of the car is careening into the driver. At this point the bones start breaking and the face is smashed against the windshield and all. And they go through this. It's like 1 microsecond, and then 1 microsecond later, and then 1 microsecond later, and you get an idea of the energy and the amount of forces that are involved in an automobile accident, that so much damage can occur in just a fraction of a second. But your text goes through and says, let's make some assumptions here, and come up with an example. It says a force of about 90,000 newtons or 20,000 pounds compressing the tibia will cause the tibia to fracture. Head accelerations of 150 Gs. That's 150 times what you're feeling right now holding you to the earth. 150 Gs experienced for about 4 thousandths of a second, or 50 times that of gravity for 60 thousandths of a second, are fatal in half of the occurrences. The threshold for damage to skin, blood vessels, and internal organs can be estimated in an approximate way by doing what's called a whole body impact area. They try to determine, if you were to take your arms, your legs, cut them off, strap them there next to you, how much of a square meter you would form. And they said that approximation for the entire front surface of your body comes out to something less than 1 square meter. 7/10 to 9/10 of a square meter forms your surface area, your front surface area. That's important when we determine forces applied to that area. If the collision lasts for less than about 70 thousandths of a second, a person will survive if the whole body impact pressure, that's the amount of force distributed over that body area, is less than about 28 pounds per square inch, or 1.9 times 10 to the 5th newtons per square meter. Death results in half of the cases where the whole body impact pressure reaches 3.5 times 10 to the 5th newtons per meter squared, or about 50 pounds per square inch. So they're setting up the parameters to give you an idea of how much surface area your body entails, something less than a square meter, and how much pressure can be applied to that whole body area over a very small amount of time, 70 thousandths of a second. Example, consider a collision involving a 70-kilogram person not wearing a seatbelt, traveling at 27 meters per second, or about 60 miles per hour, who comes to rest in about 100th of a second after striking an unpadded dashboard. Using then to calculate the forces, our definition of the impulse momentum, the difference in the momentum before and after the crash. So if we use that definition and that duration of time, 75 kilograms times our 60 miles per hour, or 27 meters per second, over the duration of the impact, gives us an average force of 2 times 10 to the 5th newtons, or about, 200,000 newtons of force being applied. Then we go back to our definition of acceleration. We defined acceleration as the interval, or the amount of velocity beginning in final and initial, and the duration of time. So since the initial value was 0, the final value is 27 meters per second, again over that same interval of time, we can see that 60 miles per hour equates to about 280 times the force of gravity, 280 Gs. If we assume the passenger crashes into the dashboard and windshield so that the head and chest, so we're not taking the whole frontal area, forgetting about the legs, waist up, combined forms about half a square meter, then in the force experienced, we find that the whole body pressure then becomes, and here's a definition that I've alluded to and we're going to use more and more, pressure is equal to the amount of force applied over the cross-sectional area, over the surface area. So that 2 times 10 to the 5th newtons of force divided by now the limited surface area we're talking about, waist up, gives me a pressure of 4 times 10 to the 5th newtons per meter squared. So let's take a look at this. 100th of a second, half of the amount, half the square meter, 280 kilograms, 2 times 10 to the 5th newtons, or about 200 kilonewtons, and the amount of pressure, 4 times 10 to the 5th newtons per square meter. $280 G's, 150 G's. So we are way above the amount of G forces that you can survive over a given period of time. Threshold for the damage of skin, the force distributed over the entire area, we chose, and we're shown that was about half of the area. If the collision lasts for less than about 70 milliseconds and the pressure is 1.9, we calculated 4, so we're way above that. And if the whole body impact pressure reaches 3.4, well, we took half of the body value. So you can see how these relationships all play into the normal amount of forces and things that your body can withstand given the amount of forces, the duration of the collision, how much surface area we're talking about, to create information that can be applied, say, in an accident investigation. Based upon what they see in the accident investigation, they can take this information, of course, backwards and determine the amount of force, then the amount of velocity, and things of this nature. Did the person really hit the brakes? And they apply other things like, do they see skid marks or no skid marks? So they use information like this to help solve accidents where there were no witnesses. The only witnesses are all there in the heap of rubble left over. So they use these relationships to help solve that. So we've seen in our introduction here an understanding of what momentum is, mass times velocity. We've seen how we create then and understand the point of impact in terms of time and impulse, and how we can derive or arrive back to the force relationships or the force involved in the problem. So now we need to look at the types of collisions that normally occur and understand something about them. Because I told you that we'd already developed our conservation of mechanical energy relationships, and there's certainly an amount of energy that goes into an impulse, momentum, in a collision. But we also need to start deriving something called the conservation of momentum. The thing we're going to learn is momentum is always conserved in a collision. Energy may not be conserved, but momentum is always conserved.